breakthroughs in research in psychiatry in the last decade has been the discovery of a lot of places in the human genome where genes have been found that seem to have something to do with how at risk people are for mental illnesses. And the biggest study to date is a study of schizophrenia. It was a study of over 150,000 people, which found many possible what we call susceptibility genes for schizophrenia. So we now have a catalog of all these genes. So this paper, which is appearing in Brain, that Danny Chen and Gianluca Ursini and other investigators at the Lieber Institute for Brain Development have done, is they've asked whether or not the genes as a group together, represented by common variations in the human genome, whether this measure of how at risk somebody is has something to do with how your brain works.
Yeah, if genetic variants work together in affecting risk for schizophrenia, we should expect that they converge on some brain function linked to neurodevelopment. And one of these functions is the hippocampal activity during declarative memory. We know that hippocampal activity during declarative memory is altered not only in patients with schizophrenia, but also in their siblings who share 50% of their DNA variation. For this reason, hippocampal activity is considered an intermediate phenotype of schizophrenia, which is a phenotype located in the past from a genetic predisposition to psychopathology.
In this study, we asked a group of healthy subjects to perform a declarative memory task. During part of the task, the subjects will view different scenes, and they have to indicate whether each picture is an indoor or outdoor scene. While the subjects were performing the task, we are recording their brain activation within fMRI.
We estimated the genetic risk of schizophrenia of each subject by using polygenic risk scores, PRS. PRS are calculated by summing the number of risk alleles and weighting each allele for the probability of association with schizophrenia, based on the results of the last GWAS. We can calculate different PRS on the basis of how we define risk alleles, and we focused our analysis on PRS6, which has the strongest association with schizophrenia. We found a negative association between PRS6 and hippocampal activity. This means that a higher genomic risk for schizophrenia corresponds with the reduced hippocampal activity during memory encoding. Genetic risk explained more than 8% of variance in activity.
So healthy subjects that had higher genetic risk activate less hippocampus, exactly as patients with schizophrenia and their healthy sibling do. The hippocampal area with strongest and active association with genetic risk is the same area of the patient and sibling activate less when compared with healthy subjects.
We then analyzed the relationship between hippocampal activity and the other polygenic risk scores, and we found that PRS6 not only has the strongest association with schizophrenia, but also has the strongest association with hippocampal activation. We analyzed the two independent samples from University of Bari and Duke University. In both samples, PRS6 has a negative association with the memory encoding activity within the right hippocampus. Overall, these findings indicate that first, schizophrenia risk alleles can converge on influencing hippocampal physiology. They also validate decreased hippocampal activity during memory encoding as an intermediate phenotype of schizophrenia.
So this in many ways represented the first demonstration of a way that genetic risk translates into how the brain works. And the translation was in a kind of working problem that characterizes people with schizophrenia. So this, we think, is one of the insights to how genes for risk create a brain of risk. It affects how the systems in the brain that keep memories in mind operate.